This is a brief resume about the paper Probabilistic Optimal Power Flow in Large-Scale Electric Transmission Systems through a Matheuristic Solution Approach. The main purpose of this work is to address the AC-OPF considering the presence of renewable energy resource. The formulated mathematical model is a multi-objective mixed-integer nonlinear programming model that aims to obtain an adequate state for control variables in order to optimize the operation of electric power systems. The optimal operation of electric power systems is intended as getting the best balance between cost of operation and efficiency of electrical supply. To understand in a schematic way, here we have the components of the model. Firstly, the objective function is designed to minimize the cost of power generation and the taxes for greenhouse gases emissions. Secondly, this minimization is performed while all the active and passive components of the system are optimized. This means that are determined an optimal dispatch for thermal, hydroelectric, photovoltaic, and wind generation, the optimal position of transformer taps, and finally the optimal position of shunt compensators taps. Note that uncertainties of wind speed, solar irradiation, and load are considered through 2m plus 1 point estimate method. This formulation corresponds to an economic environmental dispatch, where the objective function has two parts as shown in each equation respectively. The resultant multi-objective function has the omega parameter in order to obtain a set of Pareto solutions and analyze them for different weights. The main contributions of this work are the mathematical model, that is a mixed-integer nonlinear programming model to address the AC-OPF problem from an environmental economic perspective. Then, a matheuristic strategy that combines mathematical programming and the variable neighborhood descent, meta-heuristic, to solve the problem. Finally, a set of constraints that work as neighborhood structures for math-heuristic approaches applicable to other problems of power systems planning. As shown in this flowchart, the math-heuristic consists in an iterative technique based on the variable neighborhood descent meta-heuristic. In a resumed way, it determines an initial solution and obtains a set of values for discrete variables. This set and the respective value of the objective function represent a candidate solution. Then, using this candidate solution and the proposed neighborhood structures which limit the search space of the model, it's possible to obtain a new candidate solution that, if it has a better value of objective function, it repeats the search. Otherwise, the algorithm shifts the neighborhood structure. Note that the process finishes when the three proposed neighborhood structures are used, and they do not improve the better obtained candidate solution. The methodology has been tested on the IEEE 300 bus system for two cases of study. In the first case, the power system has thermal generators only. For the second case, is considered the presence of thermal, hydraulic, wind, and photovoltaic generators. The planning horizon comprises 1 year, and 11 Pareto solutions are obtained by varying the omega parameter from the objective function. This variation is performed between 0 and 1 with steps of 0.1. In this table are visible the percentage of reduction between case 1 and 2 for generation cost and greenhouse gases emissions respectively, at each value of omega parameter. It is visible that as omega parameter diminish, the percentage of reduction in generation cost as well as greenhouse gases emissions increase for the three load scenarios. The previous results of load scenarios 1 and 2 are shown in these Pareto curves, where the reduction in generation cost as well as greenhouse gases emissions are appreciable. Finally, as conclusions, it can be mentioned that the proposed methodology is adequate to solve the problem, although its complexity. The environmentally economic approach is an adequate manner to address the ACOPF, aiming to increase the renewable and clean energy.